Large language models can now output syntactically correct functions for complex algorithms in milliseconds. As the cost of implementation drops toward zero, the primary bottleneck in software engineering has moved toward high-level architectural design. Modern engineering focuses on system design, the orchestration of APIs, databases, and network routing, required to ensure disparate components function as a cohesive whole under heavy load. Every complex system starts with a single monolithic server handling every workload: the web app, APIs, and the database. As user demand increases, this single point of failure buckles. The hardware hits its physical limit, causing the entire application to drop requests and go offline. Surviving scale requires engineering our way out of this failure through strict decoupling, intelligent routing, and granular access control at the perimeter. Mastery is found in defining the rules for how thousands of machines communicate, rather than simply writing the code that runs on one of them. When a monolithic server maxes out, vertical scaling, adding more RAM and CPU to the existing machine, only delays the inevitable. Hardware upgrades eventually hit a mathematical ceiling where no more resources can be physically added. Horizontal scaling solves this by replicating the server nodes. We distribute the workload across multiple identical machines running in parallel. Replicating the servers creates a routing problem. Client devices do not know which specific node to contact. We introduce a load balancer to intercept all incoming traffic and distribute it across the available pool. A round-robin algorithm provides the simplest distribution, sequentially handing requests to each server in a rotating order. For sessions of variable lengths, sequential routing is inefficient. A least connections algorithm monitors the active load and directs new traffic to the server with the fewest ongoing sessions. If a server node goes down, any stateful session data stored on that machine is lost. To maintain persistence, we must map specific user IP addresses to the same server node for the duration of their session. This is achieved through a consistent hashing ring. As this model demonstrates, we use a hash function to plot incoming IP addresses and server nodes along a circular space, mapping each user to the nearest adjacent server. When a server fails, the ring self-heals. The load balancer automatically reroutes those specific IP points to the next available server on the circle, preventing a total session reset. Horizontal scaling without these routing algorithms only distributes the failure rather than solving the capacity constraint. Even with a stable web tier, a system remains vulnerable if every application server is fighting for the attention of a single congested database. We must decouple the data tier from the application logic, allowing the database to scale on its own independent infrastructure. Relational databases, or SQL, use a rigid table structure. This architecture is designed for complex join operations, allowing the system to merge disparate datasets, like customers and orders, with mathematical precision. SQL is the requirement for financial transactions, where ACID properties are mandatory. It ensures that every step of a transaction succeeds, or the system rolls back, locking the state to prevent data corruption. Non-relational, or NoSQL, databases prioritize flexibility. Data is stored in fluid, JSON-like documents that can expand with new asymmetrical fields without requiring a complete schema migration. By removing relational constraints, NoSQL allows for ultra-low latency and easier replication across multiple distributed nodes. Every database selection is a negotiation between conflicting needs. Architects must decide which technical trade-off, strict consistency or infinite scale, their system is designed to survive. System throughput is ultimately dictated by the invisible protocols that govern how these decoupled nodes communicate. At the transport layer, TCP provides a reliable baseline. It uses a three-way handshake to establish a connection, then guarantees that every packet is delivered in its original sequential order. UDP sacrifices this reliability for speed. There is no handshake or reordering. If a packet drops during a high-speed live stream, the system simply moves to the next one to minimize latency. Above the transport layer, API contracts define how data requests are structured and interpreted. A standard REST API utilizes fixed resource endpoints. This often results in overfetching, where a client must send 3 separate requests for users, posts, and followers, receiving large, unnecessary data blocks in each response. GraphQL eliminates this inefficiency. It allows the client to request only the exact fields required, consolidating the data into a single custom-fitted payload. For internal communication between microservices, gRPC provides an even faster alternative, using protocol buffers over HTTP2 to compress data to its physical minimum. These choices in protocols and APIs set the ceiling for a system's performance before any product features are ever implemented. Opening these communication channels to the public internet makes the system a target. A decoupled architecture is only as resilient as its perimeter security. A web application firewall and rate limiting form the first line of defense. This perimeter filters out malicious injection patterns and DDoS floods, while permitting legitimate user traffic to reach the load balancers. Traffic that passes the firewall must then undergo authentication, the process of strictly verifying a user's identity. Modern systems avoid stateful sessions that bottleneck the database. Instead, they use JSON Web Tokens. These stateless tokens contain a header, a payload of identity data, and a cryptographic signature. The gateway localizes identity verification. It mathematically validates the cryptographic signature to confirm the user's identity on the spot, removing the need for a database query. Identity is not the same as permission. Authorization is a separate logic layer that determines which specific actions an authenticated user is allowed to perform once they are inside the system. To manage third-party access securely, we use the OAuth 2 framework. It provides delegated access to specific resources without requiring the user to expose their primary credentials to the external application. Confusing identity with permissions is the primary source of catastrophic data breaches. Resilience depends on keeping authentication and authorization strictly distinct. Viewed as a single topology, we see the complete lifecycle of a request. It passes through the firewall, hits the hash ring of the load balancer, reaches the application API, and finally accesses the decoupled data tier. Specialized infrastructure at every step ensures the request remains secure, the routing stays persistent, and the data remains consistent. Every decision in this architecture, TCP versus UDP, SQL versus NoSQL, is a calculated trade. System design is the continuous management of these technical costs. Senior engineering requires looking past the individual lines of code to understand the logical and physical infrastructure required to sustain them at scale. The future of technology belongs to those who can architect the systems that make the code possible.